on a new subject of ceramic synthesis, alkoxide based sol gel processing. Now, if you remember, in the very early stages I had introduced it very briefly just to prepare ceramic powders. But here I shall be talking of using alkoxide based sol gel process for fabricating bodies. It can be a monolith, it can be a fiber, it can be a coating, anything. For example, this spectacle lens of mine which you are seeing is made up from plastic fibers. It is lightweight. Plastics are very scratchable, and dust, oil, moisture does get on the lens. So, if I try to wipe it, the dust which is very hard would scratch the lens. So, what is done? The surface of the lens was hardened. This was done by dipping it in a solution which had an alkoxide, and there is a very hard coating on both the surface of the lens. So, in alkoxide based sol gel processing, I shall be talking of monoliths. In fact, even as I talk to you, you can see the reflection of my lens and you can see the reflections of multicolored. That is simply because of the varied nature of the coating. I shall be, these are used for fibers, optical fibers, refractory fibers, and also various level of electronic, magnet electronic applications. But before I start on the real part of the alkoxide based sol gel, I need to define what is a sol and what is a gel. But before I go on to define what is a sol, I need to really define what comes before the sol. If we look at this bottle of mineral water which is there, this bottle has water and they say with added minerals. Is it a solution or is it a suspension? This one is a solution because the minerals have dissolved in the water. However, this particular material, the first thing, a disclaimer, the name on the brand on the label does not mean that I am supporting or trying to sell the product. It is just trying to make a point. What is the fundamental difference between this bottle of water and this particular antacid? This particular antacid has, if I read off, magnesium hydroxide, dried aluminum hydroxide, these are all powders. And how are they kept suspended? If I take some clay, take it in a bottle and shake it, I will find first a turbid liquid and then everything will settle down. But this one, even if I just have not shaken it for hours, in fact, it was lying in the medicine shop for days or weeks, I do not know, but you can see that it is an uniform suspension. What would I call this? This is suspension. What makes these particles? As I said, it has aluminum hydroxide, magnesium hydroxide. Aluminum, magnesium hydroxide or any of these are powders which normally if you shake it with water they will fall down. Now, why this does not fall down, why does this not flocculate is I will take up in another subsequent lectures where I shall talk of colloidal processing. Talking of colloidal processing, what is a colloid? Let us take up that fundamental distinction. You see, in this particular bottle, the powders are dispersed evenly throughout the another substance, water, and this I would call a colloid. So, one substance dispersed evenly throughout another substance. Necessarily, a colloidal system has got two separate phases. In this particular suspension, the magnesium and aluminum hydroxide are a solid phase, while the water is the continuous phase. A colloidal system now can be solid, liquid or gaseous depending on the phase. This is a liquid colloid. Let us look at others. One of the things that these colloids do is exhibit a Tyndall effect. Means if I have a suspension, and I shine a light beam through, it will be scattered all around. For those of you who have seen light coming through through a crack in a smoke filled room, you will see that you can see the light tracks, because the light is being scattered by the dust particles. Or even when there is a huge dust storm, you will see that the light is being scattered by dust particles. Of course, the best example of light being scattered is possibly during the sunsets, when you got various hues of colors, and that is due to scattering. This is called the Tyndall effect. Now, this true solution which I had talked of, this bottle of Bisleri, this has particles less than 1 nanometer or 10 to the power 3 picometers, and hence they are so small they cannot scatter light anyway, and that is a true solution. For colloids where they have solute particles dispersed in water, they can be in a range from 10 to the power of 3 to 10 to the power of 6 picometer. For example, let me take this case. Now, I bring in another one. This cold drink, I enjoy it during summer. Again, this is not a brand I am recommending or selling, it is just that I happen to pick it up. I could have picked up any other brand. What is the difference between these two? This is translucent. It has got light that cannot go through it, but this one is a bit transparent, light can go through it. So, what is the fundamental difference between these two? Here one can say that, hey, you have got particles in much finer concentration, smaller concentration. True, I have got particles in smaller concentration, and somebody will say you have got larger number of particles out here. True, the concentration can be high, but also there is a huge size difference. Here I am looking at particles which are roughly at about 10 to the power 3 picometers or 10 to the power 2 picometers. 10 to the power 3 picometers means a nanometer, 10 to the power 2 picometers means 10 nanometers. Whereas here I am looking at particles which are 10 to the power 6 picometers, that is 1000 nanometers or less. And these two are colloids. If particles are larger than 10 to the power 6 picometer, or in your terms 1000 nanometers or 1 micrometer, they are suspensions. Technically, I would say this material is a colloidal suspension. That is, here the particles are much larger than here, yet they have been kept suspended. You see, if you ask those of you who are in college now, if you had taken the same product, say when you are in schools 3-4 years ago, normally what it would read on the label, shake well before use. Why? All these particles would have coagulated at the bottom. Today the same material is marketed so that it does not coagulate. Why it does not, that is a subject of colloidal chapter I will cover, but I wanted to bring it here because of its importance. So, here today we have a colloidal suspension, a stable colloidal suspension. But before I go to this more on the colloids, let me introduce one more type of suspension. Again, this is not recommending any brand name. This particular one, you can see it is transparent. For those of you to drink it, it is transparent. And you think this is a solution. The answer is no. I hope I can find out what it has. Apple juice is one important thing. Now, apple juice has fibers, it has got other molecules. So, this apple juice which you have, this suspension which you have is strictly not a solution. This has fibers and other small chain molecules suspended in the liquid, and yet it is clear. Technically, this is what I would call a sol. A sol would be a suspension of very fine particles in a liquid, yet it would be transparent. Let me take up the gelling part a bit later. Let me talk of the types of colloids which are there based on states of matter, because in this alkoxide based sol gel processing, I would use the sol gel process to make a sol which is transparent, gel it to a transparent body, and also by a different route make it into a basically a colloid suspension, and then form it into some other type of body. If I am going to look at the colloids based on the states of matter, we have foams which is basically gas dispersed in liquid. I have given the examples over there. You have solid foams like the styrofoam, the pumice stone which you buy from the market during the winter to scrub your foot. What does it have? If you look at it, it is gas dispersed in a solid. What had happened was, during volcanic eruption, the rock melted, the huge amount of gas percolated inside that molten rock, it came out, and that is what is pumice stone. That is gas dispersed in a solid. Now, note that I have not used gas dispersed in gas, because all the gases are soluble. The third type is the aerosol, which is a liquid dispersed in a gas. For example, the fog, which is ultrafine droplets of water vapor dispersed in air, the mist, all your body sprays, they are liquid dispersed in a gas. Emulsion. Emulsion is basically liquid dispersed in liquid. For example, if I take say kerosene and water or oil and water and shake it very well, we will see that at first a very cloudy liquid, and then they separate out into kerosene and water phase. However, when we look at milk, what do we see is a stable suspension, and that has been done by emulsification. So, liquid dispersed in liquid examples are milk, mayonnaise, for those of you who love creams, gas dispersed in a solid, your butter is the best example, the cheese is the best example. Liquid dispersed in a solid, is a superb example. I do not know how many of you take Jello, so that may not be very familiar. But for those of you who have someone in the family who suffer from constipation and they take isabgol, what they do is take the isabgol, put it in water and let it stand, it forms a gel. That is what gel is. So, now I have defined, stated, given examples of what already as gel is. When solids are dispersed in a gas, there is smoke. Solid dispersed in a liquid. The best example is your the inkjet printer ink. It is the pigments which are dispersed in the ink. Blood. Now, here is a debate. Let me be very clear. I would treat blood as a sol, because here the hemoglobin particles are dispersed in the blood, in the liquid in the blood, and that I would treat it as a sol. This is a solid dispersed in a liquid. And finally, solid sols, that is solid dispersed in a solid. And here you have got examples like pearl. Paper is a superb example of a solid dispersed in a solid, and porcelain, the cup from which you drink, that is an excellent example of solid sols. Now, here in this slide I have given you examples of sols: air, liquid dispersed in a gas, the aerosol; liquid dispersed in a liquid, I have said emulsion, but I will take you there. For example, I will take you there, and solid dispersed in a liquid, that sol also I have defined. What is it? I have a link at the bottom and I hope you have time to copy it. The red color you see is the color of a gold sol. It is transparent, colored red, and if you look up the link I have given over there, you will see that the color of this sol changes with the size of the particle. And you can have a variety of colors just by varying the particle size of this gold sol. I hope you have time to copy your link, and that is why I am going quite slow. Now, having defined what is a colloid, what is a gel, what is a sol, let me pick up now on what is basically sol gel processing. You see, if I have a beaker with a liquid in it, and I have a beaker with a liquid in it, and I have particles dispersed uniformly throughout the beaker. They are stable, like some of the ones I had shown you before. These particles can assume structures like this. Where they form a network. They have, some of them have coalesced, and they have formed a network. Obviously, the particles here are larger than here because they have coalesced. Over here, if these particles have formed a networked structure, then this sol would convert to a gel. I had given you examples of gel earlier. A gel basically has a network structure of particles with liquid in the intervening spaces. That is a gel. Now, if I look at alkoxide based processes, the first thing is, let me focus on only one, TEOS, which is tetraethyl orthosilicate, because plenty of work has been done on it, and yet processes are being innovated. The structure is the silicon is bonded to 4 ethyl groups through oxygen. If we take this material with, let me say, water ethyl alcohol let me say I would take the eutectic mixture and then it is allowed to hydrolyze. What I mean is over here, for brevity's sake, the C2H5 group I am referring to in this overhead as R group. What would happen? The water would hydrolyze and I would get HOSiOR3, releasing an ethyl alcohol because R is C2H5. One of the reasons why we added ethyl alcohol over here was because at the end of the hydrolysis, one of the products would be ethyl alcohol. So, if I add ethyl alcohol in the mixture, one of the things that I have is I am controlling the rate of this reaction, I am slowing it down, so that molecule by molecule hydrolysis can occur. Now, what can happen? Two things can happen. I have not yet defined what condition. So, two things can happen. One is this particular OH-SiOR3 can undergo a condensation reaction with another similar OH-SiOR3 to give you a dimer, which I have shown over here in this screen, releasing another molecule of ethyl alcohol. So, this is a condensation reaction where two monomers, hydrolyzed monomers, have reacted with each other to form a dimer. From this dimer, lot more things can happen. Now, a dimer can react with another monomer to give you a trimer. For example, OR3 SiO SiOR3 can react with another of these two. Sorry, sorry. Two of these can react to give you a tetramer, or this can react with another TOS to give you a trimer. So, this is how one way polymerization can proceed, or something else can happen. All the OR groups may hydrolyze to give you SiOH4. In fact, both are possible. The first one, condensation reaction occurs leading to formation of polymer when it is acid catalyzed. When over in the mixture tetraethyl orthosilicate, water and ethyl alcohol mixture, I add an acid. When I am doing acid hydrolysis, I will have polymerization as I have shown on the screen over here. The degree of polymerization can vary, but I will take that up shortly. You see over here during acid hydrolysis, what has happened is basically this has been protonated, leading to this particular one, just as I had shown over here. Whereas, if I go to base hydrolysis, this is what happens. This is a nucleophilic attack, it is a backside attack, and the acid hydrolysis is an electrophilic attack. Now, with this was in presence of base. So, here what we have is the base has attacked from the backside and removed this. If at the second step, what would happen is a second OR group would go, and what I am left with is this, that at the third step I would get OH, Si, OH, and finally the last OR would go. So, here I would get SiOH4 primarily by base catalysis, which here in the case of acid catalysis I will not get it. What will happen? As I had shown over here in this slide, they would form condensation polymerization, leading to formation of dimers and tetramers. So, in acid hydrolysis I get polymerization, whereas in base hydrolysis I got heavily cross-linked clusters or polymers of SiO minus, which I have shown in number 3. So, the two reactions, the two hydrolysis reactions are entirely different. The acid catalyzed would lead me to formation of polymers, and the base catalyzed would lead me to heavily cross-linked clusters of SiOH4. Essentially, what I now have is, if I have done the hydrolysis of TEOS, hydrolyzed under basic condition, I would have huge clusters of SiOH4. I would have clusters of SiOH4, whereas if I am looking at TeOS hydrolyzed under acid conditions, I would have polymer chains dispersed in a liquid. All of this would be liquid, something like what I had said over here in this appy. In this particular one, I had said I have fibers of apple which are dispersed in liquid, and this is what I would get, the type of sol I would get if I have hydrolyzed TeOS under acid conditions. So, now having realized that base catalyzed reactions give me basically clusters of SiOH4, while acid catalyzed TeOS gives me a sol, what next? What do we do with it? Now, let me again go back to the point where I said I have a liquid and they have formed clusters, or rather this is wrong diagram. See, they have formed this cluster. Let me say this is rigid enough to be called a gel. My question is, can these form a gel, the acid or the base catalyzed one? Yes, both of them can form a gel, but with two different ends. You see, if I have a stable sol, which can be converted to a gel, as in alkoxide based sol gel processing. This opens up huge possibilities. For example, if this gel, or let me start from this sol, I take say a glass slide, a thin glass slide or a glass rod, for example, this pen even, and I dip it into it. That is, I dip the pen in and then pull it out. Now, if this is the pen, I would see the particulates sticking to the surface of this pen, and what I would see, if this is the surface of the pen, I would see a dense collection of particles which are adhering to the surface of the pen. What has happened? It is simply that when I pushed the pen in and took it out, the liquid stuck on the surface of the pen along with the particulates came out. As the water alcohol mixture evaporated, the particulates rearranged themselves to a very, very dense structure. Now, if, what if instead of dipping into this sol, I take this gel, I take this gel and dry it by evaporation. All the ethyl alcohol, water would evaporate. The size, firstly I would see a decrease in volume. So, what would happen if this was the first level of the gel, dry, the volume would decrease, we dry it more, what we will land up with? A small dried mass. Now, usually we will be extremely lucky if we get a small dried mass. Normally what happens, because evaporation is occurring from the top very fast, no evaporation is occurring from here. What happens is, after some time, when most of the liquid has gone out, leaving some residual liquid over here, differential stresses develop, and as a result, during subsequent drying, this cracks up. We will be extremely lucky to have a solid body unless we are controlling the evaporation rate, more on which I shall talk later. Now, this sort of a gel is called a zero gel. If you go to Google Images, type in zero gel, you will have lots of examples of what zero gels are. Today, we have the technology for getting zero gels of a particular shape, but I shall take that up in the next class. Now, why did this gel over here become this small? It became this small because as the liquid evaporated, the surface tension pulled the particles together, the volume decreased, and finally, when all the solvent went off, it was reduced to this smaller mass, which is the zero gel. But if you do Google Images and instead of zero gel, type in aerogel, you type in aerogel, and you see what you will see is, you will see huge number of images. Aerogels are masses where I had told you much earlier that it is solid foam. I had said gas dispersed in a solid. Under solid foams, I had written the term aerogel. Today, aerogel technology is a huge technology. Why? It is a gas dispersed in a solid. The picture I had shown of a gas burner heating a plate on top of which a rose is there. From the color of the flame, we know that the temperature there is minimum of 1800 degree centigrade. So, an 1800 degree gas torch hitting a surface, and yet the top surface does not get hot or hot enough to wilt a rose, shows how fantastic a thermal insulator it is. Aerogel today forms the backbone of space suits which are worn by spacewalkers. It has a very excellent thermal insulator. Aerogels are lighter than air, and one of the other advantages is that in space when they are walking, there is space dust, micrometeorites. This aerogel has so much of gas inside the solid, they form an excellent shield to protect the astronauts from any of these hits. In fact, if you Google Stardust mission, under Google Images, you will find that NASA and JPL, Jet Propulsion Laboratory, has just concluded a Stardust program where they sent up a sheet of aerogel up in space to collect remnants of space dust micrometeorites which would hit it, and they brought it back for analysis. So, this aerogel which I had talked of earlier with a solid foam is an excellent material, thermal insulator, gives protection against ballistic impacts. The one single question I will deal as the last item of today's lecture is, can I convert this gel into an aerogel? Firstly, I had a gel which was basically a network structure of arranged molecules or polymer chains which had huge amount of solvent occluded in it, but it was rigid enough so that it formed a gel. Now, if you are looking at gels, many of you use hair creams, those are gels. So, this is a gel. My simple question is, I want to convert it into an aerogel. It means I want to remove the solvent and replaced by say air, which is the aerogel picture I showed you courtesy NASA. Is it possible to do it? The answer is yes. And the method is, what is done is hypercritical drying. In fact, I had introduced this briefly earlier. That is, wherever the arrow is, that is the supercritical point. If I am above near the pressure or temperature, the liquid behaves as a gas. I had already said that. So, now if I take this gel and subject it to supercritical drying, or hypercritical drying, all the solvent in these spaces would no longer remain a liquid, but would be converted to a gas. Just I had showed you on the screen. I can remove that gas now without, because now the liquid is no longer there. Unlike the case here, there is always a liquid over there. The liquid is evaporating, the surface tension is drawing the particulates of the fibers together, and so it is collapsing. But here in supercritical drying, there is no liquid. I have kept it at a temperature where the liquid is all gas, and as a result, what do I gain? Here the gel structure does not collapse. Why? Because I do not have a liquid here. The liquid has not evaporated. I have subjected to a condition where the liquid has turned to a gas. Now, due to intellectual property IPR requirements, I cannot show you a hypercritical drying vessel available in open literature. It is certainly not there. But those of you who are interested, look up Google images and see hypercritical drying. You get plenty of images over there of the hypercritical drying equipment. So, what is done over here? This gel is heated above the supercritical temperature, and then the solvent is replaced with carbon dioxide. Now, carbon dioxide also is a dry ice. So, it is a gas at any of these temperatures up above. So, first of all, it is heated to above the supercritical temperature. The solvent is removed and carbon dioxide is gradually put in, and finally, the whole thing is cooled off. And what you land up with is the aerogel. The fundamental difference between again an aerogel and a zerogel, I would say, is in a zerogel I have a dense agglomeration of the particulates or the chains. In an aerogel, I will have a very porous media of the type I had showed you. I shall pick this next lecture up as to how we use sol gel processing for making shapes, coatings in the next lecture. Thank you.